When people talk about AI chips, they usually picture GPUs, huge boards, hundreds of watts, trillions of operations per second. But a robot doesn't run on AI chip. A robot runs on entirely new silicon nervous system. One chip to sense the world, one chip to understand it, one chip to decide what to do, one chip to move muscles, one chip whose only job is to stop everything when something goes wrong. If any of those chips fails, the robot fails. So today, let's stop treating robots like laptops with arms and break down clearly and practically what chips a real robot actually needs. Hello and welcome back to Chips Weekly by Diana. I'm Diana and today we are opening the robot up. The biggest misconception in robotics is this. People think robots are powered by AI chip. They're not. Robots are powered by a stack of specialized silicon, each layer solving a different problem dictated by physics, power, and safety, not software alone. Once you understand this stack, you understand why GPUs alone can't work, why robotics is so hard, and why a new class of chips is emerging. Let's start at the bottom. Before a robot can think, it has to sense. Modern robots use multiple cameras, depth sensors, force sensors, microphones, and motor encoders, all producing continuous data streams. A single high-resolution camera can generate multiple gigabytes per second of raw data. The data can't go straight to AI. First, it must be filtered, synchronized, and corrected, and time-aligned. This is handled by sensor processing silicon such as image signal processors and DSPs. These chips operate under hard real-time constraints. They don't need to be fast. They need to be on time. And if sensor data arrives late, the robot's understanding of reality is already wrong. This layer is invisible. But without it, nothing else works. Once sensor data is clean, the robot needs to understand what it's seeing. There is where AI inference happens. Perception chips run neural networks for object detection, human recognition, depth estimation, and environment mapping. Unlike data centers, robots don't train models. They run inference continuously on the tight power budgets. A data center GPU may consume 400 to 700 watts. A robot AI accelerator typically operates between 5 and 30 watts. That massive gap is why robotic perception silicon focuses on performance per watt, low latency, and predictably not raw throughput. Its job is simple but critical. Tell the robot what is happening right now. Seeing isn't enough. The robot must decide what to do next. This is handled by general-purpose processors, usually CPUs, running planning, logistic, and coordination software. Planning involves branching decisions, priorities, and exceptions. This isn't matrix math, which is why it doesn't belong to GPUs. Decision chips typically run in 1 to 3 GHz range and act as a robot's cognitive core, coordinating perception, motion, and goals. This chip answers the question, what should I do next? Now we reach the most unforgiving layer, motion control. Motors do not wait. Robots rely on real-time motor control microcontrollers running control loops at thousands of cycles per second. These chips manage torque, speed, position, balance, and force feedback. Here, even millisecond level delays can cause instability or mechanical damage. That is why motion control runs on deterministic real-time silicon, not GPUs and not high-level processors. This layer doesn't care how intelligent the robot is. It cares whether the robot stays upright. Every serious robot has one final layer, and it outranks all others: the safety controller. This chip monitors power draw, temperatures, joint limits, emergency stops, and communication failures. If sometimes goes wrong, it can cut power, freeze motion, and shut the system down entirely. Crucially, this chip doesn't trust AI. It runs simple logic designed to enforce physical limits. When safety says stop, everything stops. Zooming out, a robot needs sensor processors handling gigabytes of data. AI accelerators delivering efficient inference. CPUs managing logic. Real-time controllers hitting microseconds deadlines. And safety chips enforcing hard limits. Each layer operates under different physics, timing constraints, and power budgets. That's why robots don't run on one best AI chips. They run on carefully balanced silicon systems. And designing those systems is the hardest problems in the robotics today. This complexity explains today's industry landscape. Nvidia plays a major role with embedded AI platforms like Jetson, widely used where strong vision performance is needed, on the tight power budgets. Qualcomm brings mobile-style efficiency and integration into robotics, appealing to serve a customer robots. Companies like Texas Instruments, ST Microelectronics, and NXP quietly dominate motion control and safety, the layers that actually keep the robot stable and compliant. And Tesla represents a vertically integrated path, designing its own chips, software, and models together for machines like Optimus. There's no single winner because robotics is not one problem. Here is the truth: robots are not limited by algorithms, they are limited by silicon coordination. The future of robotics won't be decided by who has the fastest neural network, but by who can integrate sensing, perception, control, and safety into coherent, power-efficient systems. This is a real chip race, so let me ask you, will the future robots be powered by one dominant processor or by many specialized chips working together? Tell me what you think in the comments. And if you found this episode insightful, please share, like, and subscribe. And as always, stay curious, stay sharp, and stay chip aware.